Well, how exciting the ability to take our network that was formerly just for data and do something Cisco calls converge that network. Take voice, take voice communications and blend them into what used to be a network for only carrying data. Obviously, when we take these networks and converge them, we're going to have some great cost savings. We're going to have great new capabilities like unifying the messaging, having emails and chats and voice calls all be unified. And we're going to experience a real consolidation of talents. I mean, it used to be that we'd have staff that were responsible for the for the voice network, the traditional voice network, and then we'd have staff for the data network. Well, it's great when we can start to have environments where we can combine all this great expertise. When voice over technologies first started, there was specific ways to do voice over specific layer 2 technologies. For example, it was voice over frame relay technologies that were being used for, surprise, surprise, voice over frame relay. There was voice over ATM. It was used to carry voice traffic over ATM environments. But the technology that really won out was the amazingly powerful and flexible voice over IP, or as engineers often refer to it, simply VoIP. VoIP is wonderful because we can end up deploying the converged voice anywhere that our IP flows. And we know that IP flows throughout the entire network infrastructure. So how wonderful we can carry the voice traffic regardless of the underlying layer 2 technology. The voice traffic can be transmitted over Ethernet LAN environments. The voice traffic can be transmitted over frame relay WAN environments. The voice traffic can be transmitted over DSL IP environments. Wherever we have the IP network flowing with its various technologies and topologies, we can indeed carry the voice traffic. The IP telephony architecture from Cisco Systems involves 4 main areas. And by the way, let me just tell you right now that as far as all of the topics that we're going to cover in CCDA, this topic is of the most limited scope, really, overall. I'm not saying voice over IP isn't important. I'm just saying that we've got one lesson on it in this chapter for you. That's it, compared to the many lessons you had on this technology. Maybe at some point down the road, we'll add some appendixes to this discussion or something like that for you in the CCDA. But it is good to know that we have a fairly limited scope here for CCDA. Maybe that's because, again, it's not because VoIP isn't important. It's because Cisco has an entire track dedicated to voice over IP technology. So, I mean, if you want to be a voice design specialist, you're going to be taking a whole bunch of courses dedicated to that art. Anyways, I hope I make this very easy for you, especially if you have no experience with voice over IP technologies. So back to what I was saying, the IP telephony architecture from Cisco Systems. We've got client endpoints. What would be an example of a client endpoint? Oh yeah, those incredible Cisco IP phones. I depicted one when we started this lesson, didn't I? Phones are remarkable. In fact, people see them and they're like, oh my gosh, I got to get one of those. People often see them in movies or television shows, because Cisco has made a big investment to advertise these things as part of movies and television shows. I remember my wife seeing one on a television show and saying, "Is that person like watching TV on their phone on their desk?" I said, "Yeah, that is a Cisco IP phone, and that is video that's being shown on their display." So really, really cool client endpoints. By the way, the client endpoints could be traditional, what we call POTS devices, plain old telephone system devices. And we'll see where there's going to be infrastructures like a foreign exchange station port, where this stuff can still connect into the infrastructure. So as you might guess, Cisco is so smart here. They can't just develop an infrastructure that is like new technology only. They've got to develop the new technology, but they've got to make the new technology backwards compatible with the existing technology. So all this fancy voice over IP stuff needs to be able to coexist with what we call the plain old telephone system stuff. Another major layer of the IP telephony architecture is the call processing layer. This is where we literally have to do all of the stuff that involves making sure the call works properly. I mean, my goodness, when someone picks up their VoIP phone and they dial a phone number, we need to accommodate for all of that addressing that has to go on with the dialed digits to actually get them to a VoIP destination. That's just one small aspect of what has to go on with call processing. The primary example of the Cisco product that addresses this call processing is the Cisco Unified Call Manager. The Cisco Unified Call Manager is a remarkably powerful, and this Cisco Unified Call Manager, it is the replacement in the voice over IP world for that traditional PBX. PBX, which is the traditional plain old telephone system device for doing all of the call processing in traditional voice environments. The third layer of the IP telephony architecture has to do with service applications. And a great example I wanted to give you of that is Cisco Unity. Cisco Unity is that tool for bringing together all your messaging. To have someone send you an email, for example, and for you to be able to make a VoIP call and listen to your email messages. How nice is that? So you pick up your VoIP phone, you call into your Unity app, and you get not only your traditional voicemails, but you get like email messages read to you. Pretty neat. And then we have the fourth and final layer of the IP telephony architecture, the voice-enabled infrastructure. And this voice-enabled infrastructure are all of those components, all of the switches and the routers, all of these devices that are built to handle this voice over IP. This, by the way, has to be backwards compatible. And like we said, an FXS port is a great example of that, where we can plug in a traditional fax machine, or we can plug in a traditional old analog-based phone so that it can still work in this new and exciting voice over IP world. Now, a very, very key technology that is required to make this VoIP thing happen is our codecs. The codec is the big magical ingredient for voice over IP working, one of the big magical ingredients of many that we'll talk about. In the CCDA exam, you are expected to have good knowledge of these codecs. First of all, what is the codec doing? Well, the codec is that very sophisticated process that's responsible for taking my voice, which is in an analog waveform, and making sure that voice can be effectively communicated over the digital network. Ah, okay. So my voice is this analog thing going up, going down, using loud speaking volume, using soft speaking volume. As I do all these different modulations with my voice, we know this creates these analog wave shapes, and there's a lot that goes on into taking these analog forms and making them digital for transmission over what was just the data network in the old days. Now, when it comes to codecs, we have a lot of choices, and it all comes down to the key trade-off of quality versus bandwidth. You see, we would want, if we had unlimited bandwidth, we would want there to be just this ideal, just this like perfect quality. We would want a call to sound just perfect. By the way, you're listening to me right now via the internet, and it does not sound perfect at all. I'm very proud of our technology that we use to get my voice to you. It sounds better than most technologies, but you're aware, you can definitely tell, you can hear distortion. You know that you're not standing in the same room to me, listening to me with that miracle that is the human ear. So there's got to be this trade-off between quality and bandwidth when we're doing these codecs. And sure enough, codecs reflect that. For example, in a local area network where bandwidth is plentiful, we might utilize a codec called G.711. G.711 has just awesome quality, but it requires a pretty staggeringly high 64K per call. Sure enough, the great high quality that G.711 gives us comes at a cost of higher bandwidth needs. G.728 comes out to about 16K per call. Wow. So dramatically, we have less bandwidth needed, but sure enough, that came at the cost of some quality. I want you to know that in the WAN environments, where bandwidth really tends to be a precious commodity, G.729 is the often used codec, and it gets the call bit rate down to an amazing 8K. Wow. So not much bandwidth required at all for the calls. That's why G.729 is the codec of choice for many wide area network environments. By the way, many of these codecs support a technology called VAD, Voice Activity Detection. You see, if you have a codec that doesn't support voice activity detection, it's pretty inefficient in that when I'm not talking, like right now, watch, I'll be quiet. Honest, I can be quiet. I know you don't believe I can be quiet, but I will. Watch, I'm going to be quiet right now. If your codec doesn't support VAD, it will consume a bunch of bandwidth for that period of silence. Yuck, that's silly. So, voice activity detection is a neat capability that can help reduce the overhead, reduce the bandwidth by not going through the same procedure when there's no voice at all on a particular call session. Now, in addition to the codecs, we have to be able to sort out the various voice over IP control and transport mechanisms. And there's quite a few of these that I want you to know. There's the Skinny Station Control Protocol. What a great name. Skinny Station Control Protocol, SCCP. And this is a Cisco invention for signaling for call setup and control in the voice over IP environment. Something that I've mentioned earlier in the course, there's the real-time transport protocol. This encapsulates additional information on your tiny little voice packets. One of the technologies that we told you about earlier in the course was RTP header compression. To take this real-time transport protocol header that's been attached to the teeny weeny little voice packet and to compress this header information. So the real-time transport protocol takes the additional header information that's been tacked onto the voice packet and it compresses it down to make the voice packet more efficient. There's also the MGCP protocol. This is a client-server protocol, and it's used to control gateways. Voice gateways, voice over IP gateways, are devices that can control who and when and how much resources individuals can have on the voice network. Another important control protocol for you to know, very important for CCDA, it's H.323. The H.323 standard describes particular mechanisms for voice over IP terminals and these gatekeepers. It's made up of substandards. For example, H.245 is providing control protocols for voice conferencing. Q.931 provides standards for our call signaling. H.255 provides standards for admission, so registration, admission, and status indications. And there's even the real-time transport protocol that is described and defined as part of the H.323 standards. So notice lots of different codecs, lots of different voice over IP control and transport standards that we need to get a handle on. I would highly recommend flashcards to help you out in the area of these voice over IP codecs and control and transport mechanisms. The other big reminder that I have for you when it comes to voice over IP is we've got to remember how important quality of service is. And that's because quality of service is really, really needed in the voice over IP environments. And it's because our voice packets are so unbelievably fragile. By fragile, I mean these voice packets are very, very intolerant of jitter. Well, let's back up. They don't like delay. Voice packets don't like delay. But even worse, they don't like variations in delay like jitter. They don't like low bandwidth. We saw that even with the G dot, which one was it? Do you remember? G.729 that would squash the packets and give us 8K only of bandwidth per call that we would need. G.729, even that is going to get really fussy if you don't have enough bandwidth to make those G.729 phone calls. So obviously voice doesn't like low bandwidth, and also voice absolutely is intolerant of packet loss. I mean, packet loss really bad for voice. Where other forms of communication, like when we're downloading some iTunes song, I mean, that's a whole different ballgame. There can be some packet loss there, and the iTunes software, it knows how to deal with it, and we don't really detect it at the end, do we? I mean, that's the thing with voice. If there's some packet loss when we're web surfing, we don't even detect it. But if there's some packet loss during a voice over IP phone call, it can sound really, really bad. Absolutely. All right, let me fake it, right? Let me give you an example of what this packet loss would be like. Here I am talking to you, simulating packet loss. See just how annoying it is in the voice over IP network. There I was muting my microphone and unmuting it, and I hope I got the desired effect of just how fragile the voice over IP traffic is going to be. Remember, we said there were 3 overall approaches to quality of service when it came to voice over IP or any quality of service environment for that matter. We said there was the approach of best effort. You'll do really nothing except dump a bunch of money into your bandwidth. Just upgrade bandwidth absolutely everywhere. We know that's not practical, so there's this differentiated services approach, and we studied that in detail. And then we said there was the integrated services approach, utilizing something called RSVP. The integrated services approach is about having the voice over IP phone call ahead to the devices and reserve the appropriate amount of bandwidth for the voice over IP call. We told you that the differentiated services approach was by far the most popular approach for quality of service today. But now I do want to add one caveat to that. One of the reasons we still do use integrated services and RSVP in conjunction with distserv in VoIP environments is we like to use integrated services RSVP for its CAC functionality. What in the world is CAC? Well, it's call admission control. Call admission control. And this is literally saying, okay, I am not going to let this VoIP over IP phone call onto the network unless there is adequate bandwidth for that call on the network. What a neat feature. See why call admission control is still something, one little piece that's commonly done out of that integrated services approach. You can also see how it nicely integrates with distserv. Let's make sure there are the resources available on the network for the call as part of call admission control and the integrated services approach. And then once we let the VoIP call onto the network, go ahead and convert over and use a differentiated services approach. Well, I hope you have enjoyed our brief but very valuable exploration into the world of voice over IP. Next up, we want to conclude the 5-day CCDA bootcamp right here at Internetwork Expert by taking a look at the wonderful world of wireless.